Okay, hello everyone. I am Mustafa Uzuner, and I will be presenting my work on performance analysis and shape optimization of a radial compressor with SU2. This was originally a project requested by MAN Energy Solutions, and I happened to work on it during my master's degree at Ozyegin University. I will do a brief introduction first, and then I will go on to the numerical methodology for the validation and verification studies I have done, and I will show the results of those. After that, I will talk about the optimization methodology and results, and then I will give a conclusion. Very simply, a radial compressor is a rotating machinery used to compress gas. And we see radial compressors widely used in industries such as aerospace, automotive, and energy. Here I show a multi-stage radial compressor example as well. In terms of radial compressor structure, there are three main parts of a compressor, and those are inlet, impeller, and diffuser. Inlet guides the flow into impeller, and impeller adds work into the flow, and the diffuser slows down the flow to increase its static pressure. CFD is a very integrated and inherent part of the radial compressor design process. The objective of our study was to evaluate the capabilities of SU2 in the analysis of compressible turbomachinery flows, and as well as in the optimization of a turbomachinery geometry. The SU2 solver first validated on two radial compressor geometries, and for that I have used a vaneless diffuser radial compressor and a vane diffuser radial compressor. Regarding the geometry optimization, a 2D adjoint optimization study was conducted on the diffuser vane of the compressor geometry used in the case 2. I have used SU2's version 7.0.6 with some minor adaptations implemented by myself. Here are the compressor flow paths. For case 1, the vaneless diffuser case, since there were no vane in the diffuser, it was possible to model the whole geometry as a single zone geometry, and the whole domain is defined as rotating. However, for the case 2, since there was a vane at the diffuser, I had to split the geometry into multiple domains and define rotating at different parts of the geometry. For the boundary conditions, SU2 has some turbomachinery specific settings for turbo settings, and one of those is the Giles boundary condition. The Giles type non-reflecting boundary condition is used at the inlet and outlet of the domain, and accordingly, total conditions and flow angles were defined at the inlet, and the static pressure is defined at the outlet. At the interfaces of the domains, mixing plane interface is used, and the walls are defined as no-slip adiabatic, and periodic boundary conditions were defined at the periodic faces, since these geometries were simulated as single passages. For the numerical methodology, I have used 3D runs equations with the SSD turbulence model. I have used first order row and upwind schemes for the flow and turbulence numerical schemes respectively. The muscle option was not enabled for the second order row scheme because of the numerical instability at the trailing edge trailing edge of the impeller blade it brought. And the constant CFL of 10 is used, and the convergence is monitored through the mass flow rates at inlet and outlets. For the performance evaluation, I have used some non-dimensional performance parameters, and those are the polytrophic efficiency, work input coefficient, pressure rise coefficient, and volume flow coefficient. I have shown the equations here as well, and the locations these parameters are calculated from are shown here as well, the inlet and outlet parts of the domains. For the mesh independency study, I have used 3 multi-block structured meshes, and I have used volumetric flow coefficient and the total enthalpy difference between inlet and outlet to evaluate the mesh independency. The relative changes between mesh 2 and 3 were below 1% for both of those parameters. Therefore, mesh 2 was selected as to be used. And the maximum Y plus value in the mesh 2 was below 10, and overall it was around 5. The cell count for mesh 2 was near 1.6 million. For the convergence behavior, running at CFL10, the mass imbalance between inlet and outlet dropped down to 1% after 2000 iterations. And I have done a small parallel scalability study for the machine I was using as well. And after 4 cores, which I was used for the simulations, we saw that the solver scalability started to decrease. For the validation case 1, which was the veinless diffuser case, I have compared SU2's results to reference CFD data and to experimental data. Overall, SU2 results agreed very well with the reference CFD. And in terms of when we compared it to experimental data for the work pressure rise coefficient and work input coefficient, we see that SU2 is quite good as well when compared to experimental results. However, when we look at the polytrophic efficiency, we see that both reference CFD and SU2 overpredicts the polytrophic efficiency of the compressor relative to the measurements. This could be mainly due to the absence of cavity flows in the CFD model, which we tried to keep it simple. So we neglected things like tip gap as well. For the case 2, which is our verification study, the vein diffuser case, there was no experimental data here, but again, when compared to reference CFD, SU2 showed good accuracy overall when compared to the reference CFD. For the optimization study, we wanted to see the SU2's out-of-the-box capabilities in terms of optimization. For that, the vein diffuser in case 2 was optimized at a single operating point using a joint optimization. Due to the relatively small size of the vein in the span-wise direction, the vein geometry was modeled in 2D. The same mesh resolutions were used for the 2D model as well. Therefore, no additional mesh dependency study was conducted. The flow scenario corresponding to the operating point with the lowest efficiency was studied, which we experienced flow separation at the suction site, as I show here in the schematic. As I said, the suction side geometry of the vane is to be optimized to reduce the extent of the separated flow region at that suction side. The total pressure, total temperature, and flow direction at the inlet were derived from 3D simulation results. The static pressure is defined at the outlet. Again, the sides are defined as periodic, and blade walls are defined as adiabatic no-slip walls. The same numerical methodologies were used as was in the 3D simulations. For the solver, however, we selected a discrete edge joint instead of runs. The freeform deformation is selected for the shape deformation method. The FFT box used is shown with the red rectangle in the schematic. Only the wall at the suction side is included in the box. I have selected the FFT camber 2D for the design variable. For the objective function, the total pressure at the outlet was given, and the drag was given as the constraint function to avoid very dramatic changes, since this was only an optimization at a single operating point, and we didn't really want to lose performance at other operating points. And these are the optimization results. The total of 20 design iterations were carried out. The area of the flow separation region is decreased by 5%, and the total pressure loss between diffuser inlet and outlet is decreased by 0.55%. The rather limited decrease in the total pressure loss could be due to the limited size of the FFT box that is restricted to the flow separation region, and due to the restricting the shape deformation by given drag as constraint. Also, a more dramatic change in the vane geometry could have resulted in performance deterioration at other operating points, as I said earlier. For the summary, turbomachinery performance evaluation and design capabilities of SU2 were investigated in this work. SU2 behaved very similarly in terms of predicting the compressor performance data with respect to a widely used commercial CFD solver. The 2D geometry optimization capabilities of SU2 were tested on reducing the flow separation region observed at the diffuser suction side, and the design iterations conducted with the objective of maximizing the total pressure at the outlet resulted in 5% decrease in separated flow area and 0.55% decrease in total pressure loss. For the limitations I have come across during this study, the numerical stability problem with the second order row spatial discretization scheme, we would see unnatural values of temperature and density at the very corner of the trailing edge of the impeller blade, which would prevent us from being able to use the muscle option. The turbomeasure kind setting in SU2 limits the user to what kind of geometries that they can solve with SU2. And in the optimization solver, some of the available objective and constraint functions didn't really work out of the box. So, however, they could, with some little adaptations, they became functional. This study was carried out in the partnership of MAN Energy Solutions. I would like to acknowledge their intellectual support, and I would like to thank Lorenzo Fabris, who is a friend of mine from Ozyegin University, for his help during the reporting of the 2D periodic phases bug that was discovered during the optimization study. And also, I would like to thank Pedro Gomez for quickly fixing the issue about this periodic phases bug in 2D, which helped us in our optimization study a lot. Thanks for listening to me.
Thank you very much. Are there any questions from the live audience here? Yes.
Yeah, okay.
Hello, thank you, Mustafa. One suggestion for you is working. We should find stimulation in the local store. And you said that the Chinese, making conversions and the steam, is possible. I agree. And that's the reason why in all our studies we only rely on the GST. So also treating the GST sense of coefficients according to the specific commercial application. So I would suggest in the future to run those computations on the GST. Our experience matter first.
Okay, so we're never sure how clear this message is to the online audience, but the remark is that JST would be a much better option than Rho.
Yeah, I can answer if you would like.
Yeah.
Yeah, go ahead.
Yeah, I have used JST as well. However, due to that the issue about the second order row scheme that I mentioned here, the same problem was preventing JST from performing good as well. So we were kind of stuck at using first order opting schemes. I have tried JST as well, so yeah.
You can provide some from the test case of, for instance, working test case with the GST or real numbers.
Yeah, so it would be great if there can be some collaboration between your group and Matteo's group to further resolve the issue. And you also had some questions, Matteo?
Two short questions. First question, how did you compute the
So how did you compute the characteristic curve? Yeah.
Sorry, I couldn't hear.
So how was the characteristic curve computed?
Yeah, what was the methodology?
Can you comment?
I couldn't understand again, sorry.
How was the characteristic curve computed?
The operating line from choke to stall.
Yeah, from choke to stall, this characteristic curve. How was it computed?
We didn't really do anything special for that point. We used the same methodology for every point.
So if I understand correctly, you started from the design point and you slightly change the back pressure. So,
Could you
can you
understand?
repeat? No, I couldn't. Sorry.
So did you?
did you change the back pressure?
Yeah, so did you modify the back pressure at the compressor to?
The way we simulated for different operating points was by changing the outlet pressure.
Okay.
Yeah.
Well, we have also suggesting implementing the national boundary condition specific communication that was much.
Okay, so Matteo suggests this using this better boundary condition, Maslow boundary condition for the turbo machinery applications. Yeah, which is available in develop, I hope. Almost available in develop. Next.
Financial question, what's the output of this work? Where do you want to go? What's the ultimate goal?
Yeah, so what's the next step in your work is the question.
My friend Lorenzo Fabris will be continuing the work here done, but I guess the future work would be to adding more stages to the simulations, or making the tip gap or return channels volutes also be modeled in CFD to be compared to experimental and other reference CFD data. And to continue with a 3D optimization rather than the 2D one.
Satisfied, Matteo? Great. So any other question from the audience here or online? Yeah, a question?
Just very short one, so you show CFD and gives one reference in which code the big code both. This is remarkable that would be really helpful. These validation results, other features, if we can add it to the validation suite, so that it would be like, which is all these validation efforts that we can somehow capture the energy that are into to the measure of the code.
Yeah.
So that just remarkable.
Yeah, so the question is actually which reference solver was used?
For the reference CFD, I think the used one was Numerical.
Numerical, okay. That's a very good solver. And the other question was actually, can this be added to the, let's say, validation test cases? Because it's always great to expand the, let's say, official list of validation test cases for SU2, or are there limitations?
I would have to check with the MEN Energy Solutions. There are some NDA restrictions on it. So I will check with them, and I can get in touch with you after that.
Yeah, that would be great. So we're running out of time. There are probably many more questions, but we have to close here. So let's thank the speaker again.